Hi. The plot of the graph of a function is a classical exercise of mathematical analysis. It consists in trying to plot the qualitative graph of a given function f of a variable x, which is a real number. In general, this problem is a very complex problem because it consists in solving many sub-problems. And so the difficulty is that you have to employ a large number of techniques ranging from solving equations or inequalities and computing limits and derivatives and then discussing these things in a coherent way according to what are the prescriptions of the theory. Now, normally, we divide this complex problem in steps. We may say that the first step is a sort of preliminary, so that consists in, first of all, determining the domain of definition of the function, so the set of x for which f of x makes sense. Then symmetries, if any, so such as even function, odd function, or periodic function. These are the main symmetries. Studying the sign of the function, so discussing and solving the inequality f of x greater or equal than 0, if possible, of course. Computing limits at the endpoints of the domain, because at the endpoints of the domain maybe something happens to the expression and this loses a meaning. So we are interested in computing the limit of f at those points. And in the case that there are limits in certain cases, we could have also this called asymptotes for the function, which are straight lines that looks like the graph of the function. So they are helpful to plot the graph, actually. Then there is a step 2, all the operations relative to the derivative. So in general, we should start discussing continuity for the function, because continuity is much larger than differentiability. So then differentiability, where the derivative is defined, and computing the derivative of the function. At this stage, we sometimes are interested in spatial limits for the derivative, because this will tell us how the function behaves at some specific points. We will see later in an example. And then discuss the sign of the derivative, solving inequality f prime of x greater or equal than 0. And this will determine the monotonicity of the function and will be helpful to determine also minimum maximum points for the function, specifying also their nature, if they are local or relative extreme points, or global absolute maximum minimum points. The next step is to provide a better figure, the discussion of the second derivative, because this provides the information about the concavity of the function. So we have to discuss the differentiability of f prime, that is where the second derivative is defined, compute the second derivative, and discuss the sign of f second. So solving again an inequality like f second of x greater or equal than 0, and this will determine where the function is concave or convex. And points where the concavity changes are called inflection points. That might be interesting for plotting the function. With all this information, we should have a very clear picture on how the function is made. Sometimes the concavity is not necessary. We may see this as a sort of detail. Now, let's see all of this on an example. Here we take this function that we consider just an average level of function for a first-year calculus course. We have arctangent of 1 over e to x minus 1 plus x. Well, you have to be always careful to the definition of the function, because here I just wanted to, highlight this point here. The domain of the arctangent, the argument of the arctangent is not clear at 100%. Someone may think that the argument is just this fraction. Someone else may think that the argument is the fraction plus x. So what is the truth? Well, if you are uncertain, the best thing is to ask to your instructor when you are at the exam and ask what is the authentic interpretation of the assignment. We may say that in general, if this is written like that, the argument of the arctangent is just the fraction, 1 over e to x minus 1. So let's start. The domain is the set of x real for which this function makes sense. Here we see that the unique problem is this denominator, e to x minus 1, that must be different from 0. No, e to x is equal to 1, so that quantity is 0, if and only if x is 0. So the domain turns out to be all reals except 0. It is convenient to have this represented as intervals, so we can say that this is equal to the interval from minus infinity to 0, 0 excluded, union with the interval from 0 to plus infinity, 0 excluded. About symmetries, well, here apparently it's not clear if there is any symmetry, so we may say just that there are no evident symmetries in this case. We will see later in the figure that this is the case. About sign, the sign it's not immediate here because if you write down the inequality arctangent of this plus x greater or equal than 0, it's a sort of mixed inequality and we don't know exactly how to handle. In this particular case, we can, however, determine the sign by just a simple discussion, which is not a general method. We may observe that for x positive, the quantity here, e to x minus 1, is positive because e to x is larger than 1. So this fraction inside the arctangent is positive, and therefore the arctangent will be positive as well. I add x, which is positive, so everything is positive, f of x is positive. For x negative, exactly the opposite happens because in this case, e to x is less than 1, so this fraction is negative, arctangent is negative, because when the argument of the arctangent is negative, the arctangent is negative. I add x, which is negative, so I have the sum of two negative numbers, the value of f will be negative. So we can say that f of x is positive if and only if x is positive. F cannot be 0 because of the argument we just shown here. Now, this is a first important thing. As soon as you have some information on this function, it is a good idea to draw this information, to put this information on a figure. Here we have the Cartesian plane. We know that the function for x positive is positive, so there won't be any part of graph of f here. So let's cancel this part of plane to avoid the temptation to plot anything here. And also f is negative for x negative, so we do not have any part of graph in this quarter. Let's go on with the limits now. We have to discuss limit at the endpoints of this domain. The endpoints are minus infinity, there is 0, and here we have a 0 left, right, and plus infinity. So let's start with minus infinity. This means that we have to compute the limit for x going to minus infinity of f of x, which is the limit of, here we may notice that the argument of the arctangent, when x goes to minus infinity, e to x goes to 0, so this denominator goes to minus 1, and therefore the fraction goes to 1 over minus 1, so minus 1. The arctangent is a continuous function, so if the argument of the arctangent goes to minus 1, the arctangent will go to arctangent of minus 1, which is minus p over 4. Then we have plus x, but x goes to minus infinity. We have finite limit plus infinite limit. The limit is infinite, and precisely minus infinity. So this means that the function might have an asymptote of type y equal mx plus q, where m and q can be computed according to certain formulas. The formula for m is the limit, when x goes here to minus infinity, of f of x divided by x. For m, we remind that in this case, m must be different from 0 and finite. It is the angular coefficient of this straight line that looks like f. So since f goes down to minus infinity, that coefficient cannot be 0. Otherwise, this straight line would be horizontal. So let's compute this limit. When we divide f of x by x, we get this quantity. Now we see that this part here, we have 1 over x that goes to 0 times the arctangent that whatever it does is bounded, so this product goes to 0, plus 1, the limit is clearly equal 1. So m comes equal 1. It is good. We have to continue to determine q. Q can be computed also by a formula, which is the limit when x goes to minus infinity of f of x minus mx, where m is exactly this coefficient 1. Now, when we compute this, since mx is just minus mx is just minus x, when we do f of x minus x, you see that this x disappears. So we have just a limit for x going to minus infinity of the arctangent 1 over e to x minus 1, and this has been already computed above. It is minus pi over 4. So we conclude that this straight line, x minus pi over 4, is an asymptote at minus infinity. This means that the function will look like this straight line at minus infinity. So this is the straight line, and we just plot in our figure. Let's continue with the limits now at 0. So since we have a behavior left-right, as we will see, it is convenient to separate the left limit and the right limit. So let's start with the left limit. X goes to 0 minus of the function. The critical quantity is this denominator. Now, x goes to 0, so e to x goes to e to 0. 1 minus 1, 0. But 0, positive, negative, this is very important for the fraction. Since x goes to 0 from the left, e to x is actually strictly less than, when x is negative, it is strictly less than 1. So when I subtract 1, this quantity becomes negative. So it means that I go to 0, but with negative values. So that's a 0 minus. That's an error. 1 over 0 minus means negative infinity. That's right. So we have the arctangent at minus infinity, which is minus pi half. And then we have a plus x that goes to 0. So this means that this limit is minus pi half. When we compute the limit at 0 plus, it is easy to recognize that it comes equal to plus pi half. So it means that the left limit is different from right limit. When we approach 0 from the left, we go down to minus pi half. When we approach 0 from the right, we go up to pi half. We can represent this in this way. I put these two little circles because the function is actually not defined at x equals 0, so these are not values achieved by the function. But the function will go there at those two values when I approach x to 0 from the left and when I approach x to 0 from the right. Now let's go at plus infinity, which is pretty much as minus infinity. Easily we compute the limit. It's very similar. The unique difference is again here. When x goes to plus infinity, e to x now goes to plus infinity. So this denominator goes to infinity, the fraction goes to 0. So the arctangent goes to the arctangent of 0, which is 0, while the other term goes to plus infinity. So the limit at plus infinity is plus infinity. So we have again a potential asymptote y equal mx plus q, where m is again the limit for x going to plus infinity f of x divided by x. The limit is the same limit we computed before, and for the same reason we get 1. For q, when we do f of x minus mx, which is now m equal 1, so f of x minus x, we get again the limit of this arctangent, and since the argument now goes to 0, this goes to the arctangent of 0, which is 0. So this straight line is an asymptote at plus infinity. And we put this on our figure. This is the straight line, y equal x, that will look like the graph of the function at plus infinity. Now we may say that the preliminaries now are over. Let's move to the derivative. So first of all, we have to discuss continuity. Well, here, for continuity and differentiability, we can apply a similar discussion. So the function f is composition of nice functions, elementary functions, which are both continuous and differentiable where they are defined. So the function f will be continuous and differentiable on its domain. So there is no issue with the continuity or differentiability. You may object, but at 0 it looks like if the function is not continuous. Well, actually at x equals 0 the function is not defined. So continuity and differentiability do not make sense. Now let's compute the derivative. This is a pretty straightforward calculation. So we have to compute, first of all, the derivative of the arctangent, which is 1 over 1 plus the square of the argument of the arctangent. And then since it's a function, we have to differentiate the argument of the function with respect to x. Plus, there is the derivative of x, which is 1. Now, when we compute this derivative, we can use the formula for the derivative of the reciprocal, which is minus the derivative of the function divided the square of the function. So we get this. Now, by doing a common denominator, first we simplify this. As you can see, we get this, and therefore summing, we get this expression. This is the derivative of the function. Now, let's come to the limit for the derivative. Where is it interesting to compute the limit? Well, the derivative, you may observe that actually would be defined also at x equals 0, but this does not mean that the derivative makes sense at x equals 0 because the function does not make sense at x equals 0. So be careful on this. So we compute the limit at the unique point where that could give some information, which is the limit at x equals 0. In this case, there is no issue because the function f prime is a continuous function also at x equals 0. And so the limit can be easily computed. It is equal to 0. What does it mean, this? It means that this is the angular coefficient of the tangent. When we approach 0, the tangent tends to be horizontal because the slope is going to be 0. So we have to imagine that, for example, if we arrive to 0 from the right, the function will go to this point, pi half, with a tangent that becomes more and more horizontal, and same at left. So this is just a little detail that improves a bit the quality of the figure we will do at the end. Now, next step is to study the sign of the derivative, f prime. Here it is very easy because the denominator is positive, so the derivative is positive if and only if the numerator is positive. Remind that we have to solve this inequality in the domain where the derivative exists, that in this case coincide with the domain of the function. Now, this is a second degree inequality in the quantity e to x, so we can easily solve. And it yields e to x either less or equal than 1 or e to x greater or equal than 2. In terms of x, this would be x less or equal than 0, but x equals 0 cannot be taken here, so x strictly less than 0, or x greater or equal than log 2. So we can translate this fact into this table where we have the intervals from minus infinity to 0, 0 to log 2, and log 2 to plus infinity. Here we put the sign of f prime, which is positive if and only if x is negative or greater than log of 2, so positive here, and negative between 0 and log 2. Now, since the sign of the derivative is positive, in this interval, on intervals, we know that derivative positive means function increasing. So we have the function is increasing here, and from log 2 to plus infinity, and it is decreasing from 0 to log 2. Now, this table may lead to think that 0 is a maximum point because the function increases before and descends after. But remind always that f is not even defined at x equals 0. So 0 is nothing for this function, while log 2 is a point where the function is defined and continuous. And therefore, decreasing at left, increasing at right, this tells that the point x equal log 2 is a minimum point for f on at least the interval from 0 to plus infinity. Is it a global minimum? Is it a local minimum? It is only a local minimum because we know that the function on this side is negative. So it cannot be, at this side is positive, so the value here, whatever it is, will be positive. And here we have values where the function is negative. So it cannot be a global minimum. It is only a local minimum. At this stage, we could even have an idea on how the diagram is made. The function is increasing from minus infinity to 0. It looks like this asymptote at minus infinity, so we may think something like this. At 0 from the right, it reaches the quote pi half. Then it descends a bit until point log 2, and then it starts increasing at 2 plus infinity, looking like this straight line y equal x. Of course, here we have not yet determined the concavity. So if we want to have a precise information concerning the concavity, we have to move to the second derivative, which is the next step. We have, this is the derivative. We have to discuss where this function is differentiable to compute the second derivative. Here there is no problem at all, and we can easily see with a little bit of calculations that the second derivative turns out to be this. Now, we can determine the sign of the second derivative by solving the inequality f second of x greater or equal than 0. As you can see, the denominator is positive, this exponential is positive, so everything is reduced to discuss when e to 2x minus 2 is positive. And this happens for x greater than 1/2 log of 2. So again, here we have a table of variation for the sign of f prime. Here we divided the intervals on minus infinity to 0, 0 to 1/2 log 2, and 1/2 log 2 to plus infinity. Because this says that f second is positive for x larger or equal than log 2 over 2. So in these first two intervals, the derivative, the sign of the second derivative, there is a typo here, will be negative, while here it will be positive. So this means that on each of these intervals, the function is concave. But notice that I cannot say that it is concave from minus infinity to log 2 over 2 because of the discontinuity point we have in 0. And at the end, we see clearly that it is not a concave function. In any case, we have seen that concave convex functions are always continuous, so that cannot be the case for the concavity from minus infinity to log 2 over 2. So the concavity holds only on these two subintervals, and then it is convex from log 2 over 2 to plus infinity. At this point, the function is well defined with the second derivative that changed sign, so this is an inflection point for f. So now this will confirm the figure we have done before, where the point log 2 over 2 is between 0 and halfway between 0 and log of 2, the minimum point. And here is where we have the inflection point. So the function changes the concavity from concave to convex. Well, that's it. I hope that this video has been helpful for you. And I suggest you just to work out a lot of exercises to become confident with this kind of techniques.